We have Michael Brown. He's a senior supervising engineer in Herndon, Virginia, office of WSP USA.
And talk specifically about chloride sampling. This topic came up within the Western Partnership during one of their recent monthly telephone calls, and we had some good discussion. There's some desire amongst the different DOTs. Not that this is anything new, this is stuff that's been done for decades, but I think there's still a bit of a lack of uniformity in how some of this work is done, and so there was some discussion about a desire to develop some standard protocols, maybe within a given DOT, or maybe even between some DOTs, as to how you go about chloride sampling. DEX was the primary focus, but you could apply this just as well to some of the other elements, kind of as Brian had pointed out in his presentation. So I was volunteered to talk about chloride sampling. I've been doing this for a while. I first started this, and this is what got me into this business of bridge preservation. I started working with Professor Richard Wires at Virginia Tech in about 1990 during the original Strategic Highway Research Program. And that was what got me kicked off. It was a very interesting summer. I did detailed evaluation and testing of 26 bridges in 6 different states across the Midwest and Mid-Atlantic, and kind of really got inspired to do this sort of work. So I'm going to sort of reach back on that experience. A lot of what I'm covering is stuff I've either learned from Dr. Wires or developed in the interim as I've done some of the similar work for Virginia DOT and others. Very quickly, the idea is just to discuss the development of, say, a common sense type approach to obtaining testing samples for chloride content, to look at how that can be used for service life. So the things I'll discuss are a little overview, and Brian kind of set the stage for me so I don't have to spend a lot of time on that, on corrosion, and then talk about the parameters for selection of locations, how you go about the sampling, your lab testing procedures, and then evaluation of the results. So a number of these concepts were touched on in Brian's presentation, and I'm just going to kind of fill in a few details as we go. So this should look familiar. This is a basic schematic of a corrosion cell. The thing that's important for our discussion here is the ingress of chlorides over time through the concrete. And then once the chloride reaches there, you know, the steel is naturally passive in the high pH environment of concrete. And so it develops this small oxide layer that essentially brings the corrosion rate down to nil. But if that pH is reduced, or if something disruptive like chloride arrives, then that passive layer is essentially breached, and you start to get localized pitting and can become more uniform corrosion. Eventually that will result in either the loss of concrete cover, reinforcement section loss, and eventually either serviceability or potentially strength issues. So looking at the evolution of chloride ingress over time into the concrete, a way to look at it is at some point you have the construction of your new element, your new deck. You've got reinforcement at a given depth, and this is typically a distribution, but for our discussion here, we'll say that it's generally, say, about 2.5 inches. At some point, you start to apply chloride. That will vary seasonally, but at a finite depth within the concrete, it tends to stabilize and becomes generally a driving chloride concentration for the diffusion process. The chloride continues to diffuse until you reach some threshold level, and there are some general values that have been used for many years, but it's important to understand again that the critical chloride threshold is a distribution for any given environment. It's affected by many things: the composition of the steel, of course, the composition of the concrete, the pH, the consolidation in and around the bar, a whole bunch of different things. So it's always a distribution. It could be different, 1 foot apart on the same bridge deck. So the other parameter that's involved in then is the effective or apparent diffusion coefficient that you get that sort of drives this process. From that, we've got a basic model based on Fick's second law of diffusion. It's not the only driving phenomenon for chloride into concrete, but it's one that we found does generally fit the overall process and is useful for projections. And so this is similar in form to what Brian presented in his presentation. So the basic variables are those that I highlighted in the previous graph. You have the concentration at any given depth and time. You've got that surface concentration that's sort of driving the process. And then you've got the cover depth, which Brian pointed out is really critical to your overall service life. And then that apparent or effective diffusion coefficient that's part of this model. One thing that's important to note is that a lot of concrete has sort of a nominal or background amount of chloride that's inherent in the original materials. And so you may need to account for that because that would not be part of the actual diffusion model. It's already there. So you would need to subtract that background amount out when you're doing this sort of modeling. So to get an idea of the amount of chloride that's ingressed into concrete over time, we tend to want to take some samples. Part of the uniformity of practice is, ideally we generate a chloride profile looking similar to what I just showed. But, in some locations, it's still common practice to just take a single chloride value nominally at the bar depth and take that and say, well, that's my information. I think you're cheating yourself if you do that. I think you really should generate the profile. Yes, it's more individual chloride titration tests, but you can get a lot more information, as Ali in the back commented at the end of the last presentation, about where you are in the process and how that process is going to continue. So a single value at a single depth doesn't give you anywhere near as much information as an effective profile. We tend to use half-inch increments as a good way to approximate. You can do it more finely, but at some point I think the return is not worth the investment in the effort. So using those individually measured values at half-inch increments, you can then plot those and fit the model. You use basically a least squares fit to fit the fixed law to the data that you've got, and from that you can back calculate the effective diffusion coefficient for the given location in your concrete, and then you can turn around and use that to project. So in terms of standardized method for sampling, it would be helpful to develop some criteria, and so this is just sort of a schematic of what I would suggest, and I've volunteered to work with the folks in the Western Partnership if they form a task group to help kind of hammer out something more detailed. But here's my initial thoughts on it. A generalized procedure, first you need to start with looking at the background data on your structure, including as-built and inspection reports. Those can be very useful in determining exactly where you need to do your sampling. You need to come up with your criteria for the number of samples, and then from that you can come up with approximate locations that you want to do your coring depending on the element and the phenomena you're looking at. Then you locate reinforcing steel, because for chloride sampling you're typically not interested in trying to touch or damage any of the reinforcement. Take your samples, extract, and then do your repairs. Then once you've got your sample, you go back to your lab or your office, you do the testing, and then calculate using the models that I was mentioning. So we'll go through a couple of the details on this. I think the pre-planning is very important in this. You need to understand before you get out in the field exactly what it is you want to sample. Based on the data that's available, you need to look at, okay, what is the phenomena that's driving your chloride exposure? What are the sources? And then you can target some of your sampling locations accordingly. Number of samples, you want to have enough that's representative, typically statistically representative, but on the other hand, if you're not doing a research project, maybe you don't want to get into as many as some of us might otherwise. As a rule of thumb, I never do less than 3 of anything. But statistically, you may need to have up to as many as, say, 30 tests to get enough control over the variability in the process. So you need to look carefully at exactly what you're measuring and how much information you think you need to get the level of significance and get your variability under control. Some rules of thumb, I would say it depends on the bridge size. Small bridges, again, I would never take less than 3 samples, but on, just a quick rule of thumb, I might take a sample every 1,000 square feet of deck. If it's a really large bridge, that gets to be kind of overly expensive, and so you may tail that back. Again, you need to look specifically at the exposure before you do that. The depth increments, I suggested the 1/2 inch increment, but you may need to adjust that depending on some of the details of your reinforcement and other parameters. The size of the sample that you take in terms of diameter as you're drilling can be important because the nominal aggregate size in your concrete can affect the result that you get. If you've got very large aggregate and you use a very small drill, you could be drilling locations that are all aggregate and no paste. And since the chloride essentially diffuses through the paste, you may not get any sense of what's actually going on. So you need to have a diameter of your core or drill bit that's at least 1.5, preferably 2 or more times the size of your nominal aggregate to make sure that you're getting something that's representative. So your location selection, certainly you want to consult the as-built documents. Some of my recommendations are, unless you have a specific reason to want to target delaminations, generally you don't want to do your profiles at delaminations because those are going to probably be filled with contaminated water and will change the effective diffusion in that localized area and doesn't give you particularly useful information about the overall condition of the element or the deck. You may decide to target cracked areas and drill in some of those areas selectively in addition to bulk concrete. Again, it depends on exactly what questions you want to answer. Think about the drainage patterns, particularly on a deck. As Brian pointed out, you might have areas, say along a parapet, that have greater exposure because either water tends to pond there or during snow operations they tend to pile the snow there, and that will hold the chloride to that location. So that can have an influence on concentrations. The same thing would be true with wheel paths. You'll have essentially salts tracked across the bridge after an event where you've had de-icing and continue to apply more salt coming across that area. So wheel paths can have over time a greater concentration than some of the adjacent areas. And then of course Brian pointed out the importance of or the effect of joints on substructure elements if you're doing your testing there. So any areas where you have potential leakage are definitely going to be areas you're going to target for sampling. It's important to understand where the reinforcement and other embedded items in a deck are located. You typically want to avoid those. So tools for that are the basic packometer or ground penetrating radar. The packometers, conventional packometers, are only good for ferrous metals, so essentially conventional steel. If you're using some of the more recent stainless, then your old packometer may not work. So GPR may be a better option there. Also, if you've got post-tensioning or pre-stressing, you definitely want to be able to locate that. And you also want to look to see if there's embedded conduits. I have personally drilled through the conduit for what's the indicator loop for a traffic light. I had no idea it was embedded in the bridge deck. There was no visible indication that there was anything there, and as I was taking a core, suddenly I was like, oh, this is interesting. So when you're doing your sampling, it's important to locate and carefully document the locations of your samples and also the cover depths right there at the location. There's nothing more frustrating than to get a chloride value reported back and you have no idea where it was from or what the depth was, because you can't essentially do the modeling you need to do without that input. So be sure you get that as you go. The actual field sampling, there are a number of ways that you can obtain the concrete samples. The conventional method is to get a powdered sample, and then that is chemically titrated. So in the past, we've done a lot with just simply an impact hammer, rotary hammer. And what we tend to do is use a very short, flexible hose and a filter assembly that just uses a simple, off-the-shelf coffee filter and a vacuum system, and essentially suck up that material as you go to depth increments. And you can use some kind of indicator to make sure you've controlled and know what depth increments you're drilling. And then collect that, put that sample into a sample container, label it, and move on. Another method is to actually take a core and then do the subsampling in the lab. I actually prefer that method because you have better control over the depths that you're measuring than you would in the field with the drilling. You also don't have to worry about, this would be very hard to do if you happen to be in an area that was wet and damp. There are a number of issues. The other thing is when you take a core, you might be able to do other tests that complement the chloride testing that you're doing on the same sample. So some things, as I pointed out, as precautions, first of all, safety first. So when you get busy out there on a bridge deck and you're coring and drilling, you get your head down and you're looking at, concentrating on what you're doing. It's very easy to kind of become accustomed to the trucks whizzing by and you just stop paying attention. And I've seen people or heard of people getting seriously hurt by not paying attention. So always remember safety first, use the buddy system, be looking after each other when you're out there working on the job site. Again, I said review your plans carefully, look for things that you need to avoid, such as conduits, pre-stressing. Mark your areas with a temporary marker. It's a good idea to mark your core or drill bit as to a maximum depth. You really want to avoid, typically, unless you're specifically planning for it, you want to avoid punching through a bridge deck as you're drilling. And I have had that happen before, where the plans actually were not accurate and I thought I had 8 inches and I didn't. And so the core I was extracting ended up luckily just on the rubble below the, on the abutment, and nobody got hurt. But you have to be careful. I've in a previous life, I had some coworkers that were taking cores in a parking garage and dropped a core on top of somebody's Mercedes. That was not pretty. Typically, if you're coring, you want to mark your depth maybe an inch or so greater than what you're actually targeting, because rarely do your cores break off level or even. You want to make sure that you've got sufficient depth to cover what you're trying to do. If you're doing full depth cores and you've got stay in place forms, typically on the top undulation of that form, you're going to hit that and drill that first, and then your drill water will disappear, and then you've gotten there. If you're actually doing an unformed deck, then you're probably going to have somebody prepared to essentially catch that core. So that's always kind of fun. Once you've obtained your sample, you want to make sure that you carefully label it, make sure it's clear where it's from, what it represents, and then provide some protection for it. So with cores, we typically wrap it in multiple layers. Again, this is not necessarily because of the chloride per se, but because we also commonly will do some other tests, corresponding tests on the same core. So I may actually look at that and do moisture content and other tests on that core to better understand the condition of concrete. So proper labeling and transport. And then of course you've got a patch wherever you place your cores. So typically we'll use a fast setting cementitious material, but various owning agencies may have preferences as to what they want you to use. Sometimes we've used polymers and other things. So be sure and confirm that with the agency. And then, for overhead or vertical surfaces, you may need something that's a no slump or dry pack type material. With decks, you have to allow for enough time for that material to set before you can open to traffic. Once you get the material back to the lab, you'll document what you have in terms of specimen. If it's a core, you may actually go through a process of measuring, documenting, observing anything. Petrographics was something Brian mentioned that can be useful just to get some general indications of the quality of the concrete, or if there's some microcracking or other defects that could be contributing to the process. So it's good to observe those samples carefully before you start to subsample. Once you do decide to subsample, there are a couple of ways again that you can prepare your subsamples. A simple way is, which is covered in the ASTM standard, cutting it into half-inch sections and then pulverizing it into appropriate material. When you're pulverizing, you're cautioned not to allow portions of the material, either the fines or the larger aggregate particles, to be lost in that process. You need to contain it all so you have something that's representative. I remember hearing a story about a study that was being done at the Research Council, and one of the technicians was asked to pulverize these for testing, and he was tired of having to try to break these rocks down, so he's just pulling aggregate out and throwing it away. And all their values suddenly spiked. They had these huge chloride concentrations, and it was because he was skewing the sample while he was doing the subsampling. So you have to be careful about how you do that. The method I prefer to do is either a grinding or a milling process, where again you can carefully control the depth of sampling. One of the things that you need to be careful of either way is that you keep the equipment clean and you are careful not to cross-contaminate from one subsample to the next, so that if you've got an area of relatively high concentration of chloride, and then as you work your way to an area of less concentration, you don't want residual chloride on your equipment to be carrying into subsamples that are of lower concentration and skewing the results. So the milling process, this is something I had set up when I was at the Research Council. It's sort of a combination of, instead of doing the pulverizing, used essentially diamond impregnated grinder blades that you would use on, say, an angle grinder. And if you need greater thickness, you can actually stack those like a dado. And then in the milling machine, we could then take and sweep that across the surface at selective depths into the core and control that very carefully. And then the powder, as you mill it, essentially is captured again through a tube into a filter arrangement, similar to what I was showing in the field. And that way you can again very carefully control depth. Once you have your powdered sample, the typical methods are to follow either ASTM or AASHTO standards. My preference is to use acid-soluble testing, although many states use water-soluble. It's important to understand the difference. The general concept is acid-soluble essentially gets the total amount of chloride in all the materials that you've sampled. The water-soluble essentially leaches over, say, a 24-hour period the chloride out of the fine material. But if something's, say, chloride bound in an aggregate particle, it may not come out in that process. I prefer to use acid-soluble because I think it's a conservative approach. It tells you what chloride could potentially be available within the concrete. But again, you may need to look at your specific application. A third method that is available and does have a standard is the calibrated specific ion probe. So you have a probe that's sensitive to chloride. You pre-digest the powder into a solution, and then you simply place the calibrated probe and you take a voltage reading, and that voltage reading is calibrated to a chart where you can then interpret the chloride value. It can be used. It's not as precise as electrochemical or potentiometric titration. So my preference is to use the titration, but it is a little bit faster method, so if you're not as reliant on the precision of the value, it is a way to get quick information. Just briefly, I want to mention a method that I've worked a little bit on, and I would love to see this evolve into a standard. This is work with Professor Tyler Lay at Oklahoma State University, where he's been using Xray fluorescence. And the beauty of this method is he can take a core and essentially cut it longitudinally so that you have a flat face, and then place it into his device, and the device uses X-rays and it rasters and scans the entire two-dimensional surface of the core. In doing that, no real significant damage is done to the core, so that can then also be used for something else. But then it captures, simultaneously it'll capture photographic image, and then it'll look at an array of atomic elements based on the XRF. And then you can map individual elements. So in this case, you can map the intensity of reflection of essentially the chloride as a function of depth. And you can get, if you were to raster this across the width, then you can get an effective concentration as a function of width. And then we've done some comparisons from some sampling where our lab had done the conventional titration and he had done the XRF and compared the results of the two. And you see a pretty good fit. Some of the variation that you see here is actually what's of interest in the XRF to me is because I said the chloride is primarily in the paste, that's where it travels, and that's the chloride you're most concerned about that's going to get to your reinforcing steel and cause corrosion. You can actually selectively eliminate the aggregate from the analysis using the XRF. Now, comparing it back then to the pulverized specimens, you're not going to get the same values. But if you really want to understand what's going on, this may, in the future, give us a better idea. So I think it's very promising. I would love to see some DOTs get together, perhaps do a pool fund or something to help develop this into a standard. Hasn't happened yet. As I said, once you have the profile information, you can use the basic model. You rearrange, as Brian had pointed out, to solve for time, and then you can essentially project where you are in the surface life and where you expect to be in 10, 15, 20 years. One of the things that we've done is each of the variables that I pointed out earlier essentially represents a distribution. They're never really single values. So using Monte Carlo simulation, you essentially can come up with either a distribution or actually essentially a list, a bucket of data for each of those variables that is relevant to the structure you're evaluating, and then use Monte Carlo simulation to do repeated results and then come up with an overall projection.
When you do the chloride profiles, you get a wide variation in the profiles, and I guess just trying to understand what you trust and where you start to say, well, I'm going to throw out this outlier, so to speak.
Yeah, so that's part of the importance of having a representative sampling. You know, more is better, but you do have to have that trade-off of what makes sense in terms of your manpower and your resources. But chloride diffusion is highly variable. You're going to get, you can, from two locations only a couple feet apart, you can get entirely different results depending on the quality of the concrete and the nature of the chloride exposure. So when you do this field testing, you're going to see some natural variations. That's one of the reasons why we use the Monte Carlo simulation to actually look at all the variability of the inputs and come up with an overall projection.
Just a real quick plug. Michael mentioned the working group. There is going to be a working group formed on this. We need experts like Michael to be on that working group. We also need DOTs that are going to be the end users of that working group. So even if you're not an expert in chloride sampling, I would encourage you to sign up for it. You can find it on the Huva app, and then there's also a sign-up list at the registration desk.
In your Monte Carlo simulation, what type of distribution you assumed for the surface chloride content and the diffusion coefficient?
In my experience, the surface chloride concentration has typically been a normal distribution. More often than not, I actually prefer to bootstrap from the actual values we have available rather than force fit a distribution. But when we have done this work in the past, that particular variable has tended to be a normal distribution. Yeah, when we have a large amount of data and we can confirm a good form for the distribution, if it's a normal distribution, then we can then actually come up with the parameters and use the form of the normal distribution as an input and pull from that randomly. If we have a fairly finite number of values, it's better to just pull from the actual values you have so that you're not assuming or skewing what's actually there.
You talked about taking a larger number of samples, and that's one of the problems we face with most DOTs. They want to take 2 or 1 or 3 chlorides from a deck. And what they miss out on is that the cost of traffic control, mobilization, getting there is far larger than the cost of taking the extra 4 or 5 chlorides. I mean, the chlorides are less than $100 each, but traffic control and everything else cost a lot more. So instead of taking 1 or 2, 3 chlorides, if they take more chlorides, the cost is not going to increase very much. So I think we need to keep that in mind.
Ali, I agree.
Hi, I've been working with some organizations about sulfates in the concrete too, because it's like a sponge. Are you involved with other salts besides chloride?
Right. So most of the work I've done here has been primarily focused on chloride. The XRF method that I mentioned would be useful in mapping sulfur and some other elements, so that could be very useful. Sulfur is also known to interfere with the chloride testing and titration. That's a caution. So there's a way, it's documented in the standard, but there's a way to account for that.
There's a nice thorough presentation of that, the sampling process. I guess some food for thought maybe for that working group. If your end goal is really to develop diffusion coefficients, kind of fit curves to the data points that really drive that are the near surface ones. And so relative to the question of do you do a half-inch thick slice or maybe smaller, might be worth thinking about doing a little bit smaller, especially in that near surface if you've got a younger deck where the chloride may not have penetrated very deep into the concrete.
Yes, particularly for younger decks, I would agree that's not a bad approach. Thank you.
The preceding was produced by the National Center for Pavement Preservation. More information can be found on the web at pavementpreservation.org. Additional support provided by Michigan State University.